Okay, great. Hi, everyone. Welcome to another week of GOCC. Today, we're happy to have Warut speak to us about Ehrhart polynomials. Before we get started, I just want to remind you of our community agreement. In short, it's that we're all learning. Everyone has something to contribute, and no one has all the answers. With that, take it away, Warut.
Okay, thank you for the invitation to give a talk at GOCC today. Today, I'm going to be telling you about Ehrhart polynomials of generalized permutohedra from A to B. So basically, I'm going to tell you how to derive a formula of polynomials of polytopes that are called permutohedra type A and B. So let's get started with the basics. Let's start with what it means to be a polytope. A polytope in Rn is a convex hull of finitely many points in Rn. And here is what I mean precisely, what convex hull mean. And these four cartoons you see here are example of different polytopes in Rn. For example, you can have a line segment in R1 here. You can have convex hull of 4 points in purple here. And you get this triangle. And so on. You get cubes. This is probably more familiar with people. And we say that a point X in a polytope P is a vertex if there is a hyperplane H in Rn such that the intersection of P and the hyperplane H give you the set of just X itself. And intuitively, vertices are the spiky points in the polytope. So I'm wondering if people can see my cursor here.
Yeah.
Okay, good. So in this triangle, you see that there are 3 spiky points. So these are 3 vertices of this polytope here. And we say that a polytope is integral if all of its vertices have integral coordinates. And in this talk, we only going to focus on integral polytopes. Okay, so now let me tell you about Ehrhart theory. If you give me an integral polytope P in Rn of dimension D, I define the T dilation of P to be the set Tp, which is defined to be a scaling, the set of scaling every point in P by T. And so visually, Tp is scaling the polytope P by T, so it's get bigger T times. And we are interested in the number of lattice points in Tp, or the size of Tp intersect with C to the n. And here is a theorem about the number of lattice points in T dilation due to Ehrhart in 1962. It says that the number of lattice points in the T dilation of P is a polynomial function in T of degree D with rational coefficients. And this is a nice result, right? And let's see a couple examples. Here, the first example, when P is this line segment from 1 to 2 in in R1, and it has dimension 1. So by Ehrhart theory, it's the number of lattice points going to be a polynomial of degree 1. And let's see if we get that. So the number of lattice points in P, there are 2 of them. And in 2P, you can see that there are 3 of them. And in 3P, there are 4 of them. So 2, 3, 4, you can guess that well, the polynomial has to be T plus 1. Nice, it's a polynomial. That's good. And here is another example when P is this triangle here. And there are three integral points in it. 2P, you get 6 now. 3P, you get 10, you can count it here. And you can check that the number of lattice points in TP going to be equal to T squared divided by 2 plus 3T divided by 2 plus 1. And yes, it's a polynomial. And you may ask why we want to count the number of lattice points in a polytope. Well, we are combinatorialists and we like to count. That's one of the reasons. And also, the number of lattice points in polytopes encode some combinatorial properties of it. For example, the leading coefficient of the Ehrhart polynomial, P, is the volume of P itself. And the second leading coefficient of the Ehrhart polynomial is a half of the normalized surface area of P. And the constant term is always 1. So as you can see here, we get 1 always. And it's not a coincidence. All right, now let me tell you about Minkowski sum and Minkowski difference. If you give me two polytopes, P1 and P2 in Rn, the Minkowski sum of P1 and P2 is defined to be P1 plus P2, which is the set of all sum x plus y, where x is in P1 and y is in P2. And let's see some example, better with example. Here are 2 examples, maybe 3 actually. The first one is my P1 is this vertical line and my P2 is this horizontal line. And I add them up and it get me a rectangle. Yeah. And this one here, you get this polytope plus another line segment, and you get something that look like this in R3. And this is also in R3, but I add a line segment that look like this, and I add them up. I get a hexagon, this vertices. And note that Minkowski sum of polytopes gonna give you a polytope. Any questions so far?
Is this related to the Cartesian product of 2 graphs or multiple graphs, these graphs?
Which one, Minkowski sum and Minkowski difference? Or
Yeah, the Minkowski sum. It looks like a Cartesian product of like the first example of those 2 graphs.
That's not how I think about it. And I don't see how they are related to partition of graphs. But maybe we can talk about that later. Maybe
Okay,
I miss, interpreting it somehow. Okay. Other questions? Okay, so let me tell you what is the Minkowski sum, the Minkowski difference now. We know what Minkowski sum is. Minkowski difference of P2 in P1 is the set P1 minus P2, which is defined to be the set of points in Rn such that x plus P2 is a subset of P1. Okay, so let's slowly think about this. Here's an example. My P1 is this triangle here in R3, and my P2 is this line segment. And the set of points in Rn, in R3, such that when x plus this polytope, this line segment, and it lies in this triangle, is this region on the right here. So you may ask, how can you think of Minkowski difference? And here's how I like to think about it. So you see this dark shade region in P1 here, which is the same, sort of the same thing as the result on the right. And it's So the way I think of Minkowski difference is that it's the region, it's a translation of the region in P1 such that when you move P2 around this dark region, and P2 still lies in P1 when you move it around this region. So let's imagine you move this line segment around this dark region and it still lies in P2, and that gives you and the result. It's a translation of this region, by the way, not that region itself. Okay, any question about Minkowski difference? Okay, seems like there is one, and here is another example where I sum them and also subtract them or do the difference. A point triangle, a line segment, and I subtract another line segment, and I get a polytope that look like this. But be careful here. Why you have to be careful? Because the order of the sum matter. Yeah. So, for example, if I happen to do the difference of two polytopes in parentheses here, you can see that this gives you the empty set, and that's gonna be bad because Minkowski sum or difference, the polytope shouldn't be, it doesn't make sense to divide it when it's empty. So yeah, you have to be careful with the ordering. So when I write, say, P1 plus P2 minus P3 plus P4 minus P5 like this, I mean that you add them first, right? You add the plus first, and then you subtract the minuses later. Mm-hmm. And in general, if you rearrange it and it never give you, and the partial sum never give you empty set, then the ordering shouldn't matter. Right? But yeah, you have to be careful when some of them give you the empty set. And a note is that Minkowski difference of polytopes is a polytope. Any question? Okay. Now we know what a polytope is, and we know a theory of how to count integer points, a lattice point in polytope. And Minkowski sum and Minkowski difference of polytopes. Now let me tell you what generalized permutohedra of type A and type B are. So let's start from A. Let's start with I have a point in Rn, W1 greater than W2, and so on, greater than Wn. Then the permutohedron Pn of W1 to Wn is defined to be the convex hull of n factorial points that obtained by permuting the coordinates of W1 to Wn. For example, I have two examples here. P2 of the point 1, 0. So this polytope is a permutohedron that obtained by permuting the coordinate 1, 0. So you get 1, 0 and 0, 1, and you do the convex hull of this point. So you get a line segment in R2. And P3 of 2, 1, 0, you permute the points 2, 1, 0 and do the convex hull, and you get this hexagon in R3. Okay. Here are some remarks that I want to make. The permutohedron Pn of W1 to Wn, this is a typo, lies in the hyperplane x1 plus ... plus xn equal to W1 plus ... plus Wn in Rn. And this implies that it has dimension n minus 1. Okay. So it's not a full dimension. And the edges of this permutohedron are parallel to ei minus ej for I not equal to j. For example, this polytope here, edges of it this is the only edge, and it's parallel to E1 minus E2. Yeah, EI, by the way, is the standard basic vector in Rn, where you have 0, 0, and 1 only at the I component. And another remark is that the normal fan, so I didn't define what normal fan is, but you're gonna be good with this talk, even you don't know this. So I'm just gonna say it in case some people are familiar with this concept. The normal fan of this permutohedron is called the An-1 permutohedral fan, whose full dimensional cones are the chambers in the hyperplane arrangement xi equal to xj, and x with I not equal to j.
Warut,
yes.
I have a question. So
yeah.
we are imposing that the W's are decreasing. So are we saying that they're, I guess, what is the purpose of that? Can I just have like, I guess, why can't I just have 1, 1, 1, 1, 1 or something like this?
Yeah, you can have that, certainly.
I guess that's just one point.
Right, it's called, yeah, it's called generalized.
Okay, okay, great.
Yeah, this is what I'm going to tell you next.
Okay.
Right, good question. You know now what polytopes are. Now I'm gonna generalize it. Generalize it to we call generalized polytopes. It's been studied a long time, and many people know it very well. And it usually just called generalized permutohedra, but I'm gonna emphasize it by putting type A, just to emphasize it. It's associated to type A. So what is it? A generalized permutohedra is a polytope whose edges are parallel to EI minus EJ for some I not equal to J. So the previous slide, a permutohedron certainly satisfies this by a remark. And yeah, this is a generalization of that. So what are they? So here are some examples. Here is you can think of W being 1, 0, 0 here. In this case, you permute this point and you get this triangle, or we call it a 2 simplex. Sorry, yes, a 2 simplex in R3. And you see that we have hexagon. And we can also have something that look pretty different from what you've seen, and something like this. The third example. Or equivalently, you can define generalized type A permutohedra to be a polytope whose normal fan cosine the An-1 permutohedral fan that I just mentioned earlier. But again, it's okay if you are not familiar with this concept. So you just take the first definition. Here are a few remarks. Generalized permutohedra are deeply related to many mathematical concepts such as matroids, Weyl groups, and graphs, for example. And yeah, that's how they are related to type A, type B, concentric groups, and things like that you have seen in other fields. That's how they got their names. And many polytopes are generalized type A permutohedra, including sonotopes, associate hedra, cyclohedra, Pitman-Stanley polytopes, for example. And again, if you are not familiar with these names, that will be fine for this talk. Any questions so far? Okay. Now for I subset of bracket n, which means it's a set contain 1, 2, 3 all the way to n. be a non-empty set, we define this delta, this triangle I, to be the convex hull of E sub I, where I is in this big I. So you're gonna get this convex hull is called simplex. So you're gonna get simplex that associate to I, right? Each subset here. And there is a theorem by Postnikov in 2005 saying that if P is a generalized type A permutohedron, then you can write P as Minkowski sum and differences of simplices. So with some coefficient here, yi, being real numbers. For example, if my polytope P look like this, and you can check that it turned out to be equal to 3 times this simplex plus 1 times this simplex and minus this line segment, which is the simplex delta 1, 3. Yeah. And yeah, let's see another one. So this hexagon here is a line is equal to the sum of these 3 simplices, which are line segment that you have seen before in one of the example previously. And Postnikov associate a bipartite graph G to each generalized type A permutohedron. For example, when P is in the first example here, this is my G. My G, how does he define this bipartite graph? He defined it to be, so how many simplices do you have? We have 3 of them, 3 different. So you're gonna have 3 vertices on the left, and it lives in R3, so you're gonna have 3 vertices on the right. And the edges between the left vertices and the right vertices are exactly the indices I. Yeah. So for example, the indices of this is the set 1, 2, 3. So you have edges 1, 2, 3 adjacent to the first left vertex. So, any question about the graph? So you can also have it for the segment.
Yeah.
Yes.
So addition of like the Minkowski addition is commutative, right?
Yeah.
Right.
But
So doesn't that mean we can have 2 different bipartite graphs depending on how we label our simplices?
that's a good question. Yes. You can have it's not unique, so you have to order it somehow. Stick with some order. Yeah.
Okay.
Good question. Yeah. But it wouldn't affect the theorems that we're gonna talk about, as you will see. Now, okay, for a given, sorry, I forgot to say that because we can do this, so we can write every generalized type A permutohedron as PG of Y1 to Ym. Right? G is the associated bipartite graph, and Y1 to Ym are the coefficient in front of each simplex. And so if you give me PG of Y1 to Ym in Rn, where Yi, so Yi, so this is a typo, is not equal to 0 for all I, then Postnikov define a G draconian sequence A1 to An to be the set of non-negative, this is also say non-negative integers that satisfy the following. So A1 plus all the way to Am must be equal to n minus 1. And the sum of Ai over subset J, J non-empty, a subset of bracket n here, has to satisfy this property. This is better with an example. Okay, for example, this is an example from the previous slide. PG equal PG of 111, which is this polytope here. Oh, maybe it's a different one. Sorry, a different one from the previous page. And you get this graph as a its associated graph. What is it G draconians? Well, you're going to have A1 to A3 because we have 3 simplices here in the summand. And A1 plus A2 plus A3 has to be n minus 1. So 3 minus 1, you get 2. And let's say A1 plus A2, it's going to be equal to the union of I1. So I1 is bracket 3 and I2 is 1, 3. And then you subtract 1 from the cardinality. So you get 2. So you do this for all of the possible combination. And you're going to get these inequalities. And you can solve it even by hand easily, that these 4 points going to be our G draconian sequences. And it turned out to be integral points in this polytope here, PG prime of 111 minus delta of bracket 3 here, where G prime is the bipartite obtained from G by swapping the left and right vertices. Any question about G draconian sequences?
This feels like the Hall's marriage theorem type conditions where you have like an inequality between 2 sets, but I don't know if it's related at all.
Sorry, can you? I'm not sure what I get.
The Hall's theorem for like perfect matching. They also have these kind of inequality conditions.
Oh, okay, yeah, right. It's the G draconian sequences is come from matching. Yes. Okay. So that's why it looked familiar to you, I think. Yeah. Okay. Good. Right. It G draconian sequences because it's associated to graph G and it's associated to the Hall marriage theorem. Yeah. You are familiar with that.
Why is it called draconian sequence?
Yeah. So in Postnikov paper, he stated Hall marriage theorem in a way that so you have n right and I think another n plus 1 grooms, and then a dragon come to town and gonna take one of them, something like that. So that's how he got the name draconian. It's from dragon, I think. Yeah, good question. Okay, all right. Here's a theorem. Let PG 1, 1, 1, 1. So we only focus on the coefficient being 1, 1, 1, 1 here, and with I1 equal to the set bracket n, and then we define P minus, and I'm gonna call it the trim, right? The trim of P, because you subtract it out by the simplex delta bracket n. Yeah? And Postnikov proof show that the number of lattice points in the trim PG of the trim of PG here equal the number of G draconian sequences of it. Let's see an example. Here is the previous example, and you trim it by delta of bracket 3 in this case. So this is my P. It look like this, and this is bracket 3, bracket delta bracket 3, and the result you get this polytope. There are 4 integral points, and it's exactly equal to the number of G draconian. You saw that there are 4 of them. And using simple binomial identity, Postnikov proved that the number of lattice points sorry, I should write the trim, right? The trim of PG is equal to this formula. And PG in general, so PG of Y1 to Ym. I should have written it, that's a typo. Okay. Well, now you know what generalized permutohedra are, and you know how to compute lattice point in it. So how do we get Ehrhart polynomials? So Ehrhart polynomial just by scaling y, right, by t. So you plug in scaling y by t in here, and then you add you add the simplex into it, right? And you plug in this formula, you're going to get Ehrhart polynomial of P. Any questions so far? Okay. Now let's get to type B from type A. A polytope P is a generalized type B permutohedron if its edges are parallel to EI or EI minus EJ or EI plus EJ for some I not equal to J. Okay. Here are a few examples. You can have a simplex that in R2 that look like this triangle here. And you can also have a hexagon that you have seen before, or a cube that look like this. Here are a few remarks. You can define generalized type B permutohedron to be the polytope whose normal fan cosine the Bn permutohedral fan, which is defined to be the fan whose full dimensional cones are the chambers in the hyperplane arrangement xi equal to 0 and xi equal to plus or minus xj, I not equal to j. Again, you are not familiar, that will be fine. And another remark is that every generalized type A permutohedron is a generalized type B permutohedron by definition. And because type A, you need edges to be in the direction EI minus EJ. Any question about them? Okay, so now let this bracket n to n bar to be this set here. And for I in bracket n, let EI bar being defined to be minus EI. Okay. And here's another definition. Let the set at S of admissible subset of bracket n bar is defined to be this set here. So it's the subset S of this set n to n bar, such that when you have I, so I and I bar are not contained in S at the same time. And yeah, at S subscript n here is the set of all admissible subset of size n. And for S in the set of admissible subset, we let delta subscript S and then a superscript 0 here to be the convex hull of 0 and EI for I in S. So this is a standard simplex in Rn. And recently, Fink, Larson, and Spink, which I would denote EFLS, show from their study of delta-matroid the following theorem. Every generalized type A permutohedron P in Rn can be expressed uniquely as Minkowski sum of these simplices. So that's a very nice result, and you should be familiar with, you probably think that it looked like the type A one, and that exactly that is correct because they try to generalize that result, and this is what they have, which is a very nice one. For example, a single point here, the point -1, 0, can be written as this delta of 1 bar and delta of 1, and you get this single point. Or this polytope here, which is a generalized type B permutohedron, Minkowski sum of this. And so we can write every generalized type A permutohedron as P of CS, right? But CS the coefficient. Okay, And then they define psi transversal of n tuple of admissible subset is to be an admissible subset T in admissible subset subscript n such that there is a bijection J from this set to T with Ji in Si or I in N. Okay, that's a lot. So see an example. Here's my PS, this example, and T is this set here, 1 and 2 bar, and then you can check that it's a psi transversal of S1, S2, where S1 is this bracket 2 and S2 is this set here. Because you can have a bijection, 1 live in S1 and 2 bar live in S2 here. And they define linear operator on polynomials. This, and then let me define this cube subscript n to be the standard unit cube in Rn, and they give the volume formula. So this is a volume formula, and they give the lattice point formula inside P minus this cube here to be the transformation of this volume. So the formula has quite a lot of terms because you can permute, because there are many psi transversal. So I thought of a way to express it in a simpler way and try to find a way that is, more similar to what Postnikov did with type A. Any question so far?
I don't know if I missed it. What are the DIs?
Sorry?
The DIs in the linear operator. Yeah.
This one?
Yeah.
Let's see. Oh, I should say, right. Each monomial. So each monomial x1 to the d1 times x2. Yeah, that's a missing information. Sorry. Right. That's what confuses you. Now, let me derive Ehrhart polynomial from generalized combinatorics of type A to type B. I'm going to tell you what the Ehrhart polynomial of the type B is. So let P be generalized type B permutohedron with Ci greater than 0. You can write it this way, right, by the previous theorem. And yeah, all of the Ci gonna be integers because we want to talk about Ehrhart polynomial. Only want to talk about integral polytopes. And for admissible T, admissible subset T of size n, we let P subscript T to be this generalized type B permutohedron. So you intersect each Si with T. Yeah. And one can think of T as an octant in Rn. For example, if T is equal to the set of 1 all the way to n, then it corresponds to the first octant where every coordinate are positive. While when T is equal to 1 bar all the way to n bar, then it's going to be the opposite octant when every coordinate is negative. And here are two important observations. PT here, P subscript T, you can think of it as a projection of a generalized type A permutohedron. And this is where tools and technique from generalized type A permutohedron comes into play. And here is another important observation. P subscript T is equal to P intersect with the octant corresponding to t. Well, let's see an example. Here's my p, look like this. You saw it before in the previous slide. It looked like this one. And if my t is equal to the set 1, 2, then it gives me the intersection of p with the first oct, in this case, in the first quadrant. Right? So I get this piece, and if my t is the opposite octant, then I get this q here, and so on and so forth. And yeah, you can check that p of 1, 2 is equal to this when you intersect this set 1, 2 with this set 3 set. And it turned out to be equal to this PG 2, 1 of where G of this graph, where G is this bipartite graph. Yeah. So you can associate bipartite graph G to every PT, because now it's a PT is generalized type A permutohedron. Right? So you can do that. Any question about this? Okay, so it is nice that you can view type B permutohedron as type A one, because now you can apply the technique that Postnikov did with type A to compute Ehrhart polynomials. To find a formula for Ehrhart polynomial of generalized type A permutohedra, we only need to find a formula for P where this Ci here are positive for all I. Right? So you don't have to find formula for the coefficient that are negative. Right? Why? Right? Because it's going to extend automatically to other cases. And to do this, we begin by finding a formula for the case when the coefficient are 1, 1, 1, 1. See here? This should remind you of what Postnikov did with type A. Right? He remember the theorem that he said PG of 1, 1, 1, 1, the number of lattice point is equal to the number of G draconian in some polytope. Right? G draconian and that associate to it. So that's the same approach here. Okay, let me give you a definition. For T, an admissible subset of size n, let D of PT, okay, PT, the trim, right? The trim one here, be the set of G draconian sequences of this trim of PT, which is PT minus delta T here, and then let the PT intersect with this Q, this MQ, to be the set of G draconian sequences in here, such that all of the AI are less than or equal to 1. Okay, so that's why I intersected with Q, because it's less than or equal to 1. And here is the main result that I found. Suppose that P look like this. Like, again, the coefficient are 1, 1, 1, 1 in Rn. Then the number of lattice points in this type B permutohedron, P minus the n cube, gonna be equal to this sum here. But what is this sum? Let me explain what it is. So so you pick T, and then you compute the G draconian in each PT, such that each coordinate AI is less than or equal to 1, and then you count them, right? And you do this for every T, and that's the number of a lattice point in this polytope here. Any question so far? Okay, well, let me rewrite that theorem again. And this implies that the number of lattice points in this polytope here is equal to this sum. Okay, you might ask why. Right? The reason is this sum, and this sum only is sum over all G draconian. Right? It doesn't restrict the G draconian to be less than or equal to 1. And why, you might ask? It's because when AI is bigger than 1, then this formula is going to give you 0 automatically. And so it's equal to what I wrote in the previous theorem. And then by this observation and with a simple binomial identity, I get the formula for lattice point in P minus the n cube as this one. So the difference from this formula and this formula is that now you have y1 to ym. Oh, that's a typo. Big typo. It should say C1 to Cm, sorry, because the coefficient is C1 to Cm. And then, well, you might say, well, you want to tell me the Ehrhart polynomial? This is not Ehrhart polynomial. But you can compute Ehrhart polynomial by plugging in t times p plus the n cube, which is equal to scaling this ci by t, and then you add other terms into this formula, and you're going to get Ehrhart polynomial of p. Any question so far? How much time do I have? Yeah.
Like 5-10 more minutes.
Okay, right. Sounds good. That would be perfect. No question? Okay, let's move on. Let me give you some idea of how it is proved. So here's an example that I used before, this polytope here, and it looked like this. Okay? And then what is p minus 2 cube? It's gonna look like this. It's gonna look like this one, and it has 1, 2, 3, 4, 5, 6, 7, 8 lattice point in it. And the previous theorem said that it's equal to the number of you sum all over integer point. Sorry, G draconian sequences. And here how it works. So you break it up into PT, which has 4 pieces like this, right? Because you have 4 quadrants. And yeah, the idea of the proof is that first we subdivide PT, each PT into 5 mixed cells. This is an application of the Cayley trick, which is a common technique for subdividing polytope that is Minkowski sum of other polytopes. And what are 5 mixed cells? They are a cell, there are regions in the polytope that in this case look like a Minkowski sum of faces of this polytope, delta subscript S and superscript 0. Yeah. In R2, there are things like cube, unit cube, and this triangle, or triangle that flip like this. And yeah, these are just rough ideas. So there are more detail into what 5 mixed cells are, but yeah, probably this what it is. And each G draconian sequence of this in here gonna correspond to a cube 5 mixed cell. So 5 mixed cells that are cube, which also correspond to a lattice point in P minus n cube. Okay, so let's see an example. So we have this PT here. Let's look at the first piece on the top right. And I claim that each G draconian sequence in here correspond to the cell that are unit cube. How many cells? There are 3 of them, and they correspond to exactly one. Each one of them correspond to 1 lattice point. So you have 3 of them here. and it corresponds to this 3 point in P minus 2 cube. Yeah. And then you do the next piece, and let's say this piece, you have 2 cube cells, and so it corresponds to 2 lattice point, and it corresponds to this 2 here. And you keep doing. You have 1 here, and it corresponds to this 1 here. And you have 2 here, correspond to this 2 lattice points here. And that's how the correspondence goes. All right, any question about this? So this is a bit hand-wavy. So, it's not very detailed. Okay, this is the last slide. Let me tell you about the future work that I'm planning on working on. So what's nice about this approach is that it allows me to see the generalized type B permutohedra in each octant. You can view it as a generalized type A permutohedra. And so you can deduce many properties of generalized type B permutohedra directly using the properties of the type A counterpart. So I can ask things that I will study for the type A one. For example, the phases, right, or F vector and H vector of the type B one, and try to use the tools and techniques that people use for the type A to compute them. So that's what I'm planning to do. And that's the talk. That's all the talk. Thank you for listening. Any question?
Well, first, let's take a bit to give a round of applause. Thank you for such a great talk. And yeah, let's start off with questions.
I have some questions.
Yes.
Yeah, so about a sign transversal thing, is there like more graph theory kind of way to think about it, like sign graph or something like that?
That's a good question. I didn't think of it as sine graph, but there is a correspondence between sine transversal and G-Draconian sequences. And G-Draconian sequences correspond to a tree in the graph G that associate to the polytope. So in some way, you can view the sine transversal, in that sense, in as a tree, just like G-Draconian sequences. I don't know if that answers your question. There is a way to associate it, but it's a bit hard to describe.
Yeah.
Yeah.
And do you have maybe some class of type B generalized permutohedron that like you can try to use these to really compute the Ehrhart polynomial, or just to simplify some of the sum you have when you are using the, yeah.
So you mean I have a formula, and is there a family that give me an even nicer formula? Is that what?
Yeah, like
okay.
Maybe some of the sum you can simplify, or because you have, yeah.
Right. Let me go to the formula. So this is the formula. I didn't specifically look at any particular families, but I think maybe I look at one, but I didn't exactly use this formula. So I derived another one for those family, and it's the mean. This family is the Minkowski sum of what do we call cross polytopes, phases of them, things like that, and you can get a slightly different formulas that doesn't look much like this, but it's a good question. So someone should maybe try to think about if you can find a nicer formula. For example, this doesn't tell you that the Ehrhart polynomial are positive for even any, the coefficients are not, positive for any family. Just directly staring at this formula. So maybe find a way to make the positivity appear would be great. Yeah.
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 Thank you.
Yeah. You're welcome. Other questions?
Maybe if there are no more questions for now, let's give another round of applause. Yeah, and stop the video.